Hi. Previously, we added the balance and public key fields to the wallet. Next, we should make sure this wallet can sign data. Furthermore, while we're at it, we're going to make sure that the wallet can verify the signatures of other wallets. After all, we don't want to accept any transactions unless the actual underlying wallet gave it a proper signature with its private key. To develop these two key behaviors, generating signatures and verifying them, we're going to head to the index.test.js file of the wallet directory and then add a new testing block. In this block, we're going to describe a situation where we're signing data. And then we'll have a callback as the second parameter. Cool. When it comes to tests about signing data, the primary piece is data itself to sign. So this can be anything. So how about a data field that says foobar? And now we can construct some tests around signing this data. First, we should be able to verify a signature. So let's say it verifies a signature. Cool. So the wallet can indeed verify a signature when there is data that is signed. Likewise, we'll construct a test for the opposite case. It shouldn't verify a signature if it's invalid. So we'll say it does not verify an invalid signature. Then we'll provide a callback as the second parameter. Cool. To verify signatures, we're going to introduce a generic method in the util class. So let's be a little psychic and predict the future, because we know that eventually we're going to introduce this verify signature method within the util directory, that is one directory back in the util/index.js file. This verify signature method is going to be able to take an incoming object with 3 fields. So when we call verify signature, we're going to pass in an object, and those fields are the public key, the data, and the signature. Cool. Now let's assign values for each of these fields. First, the public key has to be any wallet's public key. So we might as well use the local wallet. So let's use wallet.public-key. The data we already have, and then the signature is going to be the result of calling a method called sign contained within each wallet instance. So in this case, the signature should be created by signing the data using the wallet's sign method. All right, nice. And overall, we're going to expect this to return true. After all, the signature was created by the wallet. So if we're verifying the same underlying data with the wallet's own public key, verify signature should return true in this case. So we're going to wrap this whole thing within an expect statement. So add the expect statement, make sure it's indented properly, and we want this to be true. So again, you may be curious how this verify signature method is actually going to work. We're going to use the ability of the elliptic module to decrypt the original data using the presented key and the signature, as well as the data itself. So the system goes like this. You decrypt the data presented by the signature using the given public key with the elliptic module. Now, if that decrypted data does not match the proposed data, well, the signature is then deemed invalid. Otherwise, if it does match, the signature is valid and verified. Now, this does beg the question, why can't someone just use the public key and signature to generate other pieces of data and other matching signatures to try and cheat the system? The answer to that is that a proper signature based off of a public key can only be created with the original key pair object that contains the underlying private key. If the signature, public key, or underlying data is modified in any way, well, bad news, the decryption is going to be off and the derived data isn't going to match the proposed data. So let's actually create this scenario in our second test. We're going to expect that if we call verify signature here, and then we're still going to use the public key with the wallet.public key, we're still going to use the data. But then we're going to try to make the signature based off of another wallet signature. So we'll call new wallet.sign data here. And certainly, if we use a different wallet, well, we should expect this verify signature method to be false. All right, great. So as we save this, we have 2 new failing tests running in the command line. First, it doesn't verify a signature, and likewise, it doesn't verify an invalid signature, and pretty much the main culprit is that don't even have the verify signature nor the wallet.sign methods yet. But let's add that now. If you're interested in doing the coding aspect as a challenge, visit this location, so indtny/elliptic on GitHub. This is the user who hosts the elliptic module, and you're going to want to find the README in order to find the relevant commands and methods to use in order to get this functionality up. So first up, let's resolve this issue where wallet.sign is not a method. In the index.js file, let's add a sign method right in the wallet class. As for the sign method's return value, luckily this key pair object has a sign method itself, so the key pair that we currently have within the wallet. It has the knowledge of the inner private key, which means it's going to be able to take some data and sign that. But we want this key pair to be available within the sign method, so instead, we're going to set this.keyPair to the result of an ec.genKeyPair. And now when we create our public key, well, we need to reference this.keyPair. And now this means that the result of the sign method can be a call to this.keyPair.sign. And this needs some data to sign, so the sign method itself is going to take a data argument and then pass that into the keyPair's sign method too. Now, there's one more aspect to this before we move on. This keyPair sign method works optimally when the data arrives in the form of a single cryptographic hash. So before this data goes into the keyPair.sign method, let's hash it. So let's use the cryptohash method at the top of the file, and we'll grab that by getting cryptohash. So const cryptohash equals a require of our util file, and then going to the cryptohash location in that directory. So util/cryptohash, one directory back. And before we sign the data, let's hash it. So we'll call cryptohash of the data. So that way we're always signing on an optimized hashed version of the data. As we save this takes care of the sign method not being defined, but now we get a different error where verify signature is not a function. Well, we still need to implement that within our actual util/index.js file. So head to util/index.js. And then we're going to add a new verify signature method. So a constant of verify signature. And to verify a signature, we have that object with the three fields of public key, data, and signature as we've created within our actual wallet tests. And then to get past this certain error, we can include verify signature right within our index.js file in util. So as we do so, now we get a different error. Instead of receiving true or false, it's receiving undefined values. Cool, this means we just have to implement the logic for verify signatures. To verify the signature, the EC instance itself provides a verify method. So this is convenient for us because our verify signature method can wrap around that verify method of EC. However, this verify method is only available within an instance of a key object. But luckily, we can create a temporary key object using this public key. So first we're going to get key from public by using the result of a key from public function in this EC instance. And all we got to do is pass in this public key and then say that this public key is coming in the hex form. So recall that we encoded this public key in its hex format. Well, we need to make sure that EC knows that this temporary key that we're generating is based on a hexadecimal public key. Nice. This now allows us to return a call of key from public.verify. And verify takes in data first and then the signature. But there's a catch with this data. This data needs to be in a hash form. Therefore, let's require the cryptohash function that is located locally. So we're going to get the result of the cryptohash file that is in the same folder. And before we verify the data, we're going to wrap this within a call to the cryptohash method itself. And as we save this, if all goes well, that final change should have gotten the test to green. Excellent. This means that we can now verify valid signatures and that we can also invalidate bad signatures. In addition, we've also tested the signing functionality by making sure that the generated signatures are both correct and incorrect if they're corrupted. Okay, cool. With that, we've given the wallet the ability to officially mark data with their unique signatures. In addition, any generic signature can be verified to check if the underlying data is correct in order to prevent fraud in the system. Next, with this signing ability, let's give the wallet the power to conduct official transactions.